Welcome to AI Research video blog number 3. Today I'm going to be talking about biases in architecture. So about biases, I'm going to be talking about why they're important, why they're great, what they are, and architecture, I'll be talking about how I actually want to design my system. So last time I talked about intelligence, and we said that intelligence is the ability to make optimizing choices. You can imagine a system which is receiving input from the world and receiving reward values. Based on what it sees about the world and what world states actually make it happy, it's going to be making outputs. And these outputs are choices that it's making, and those choices are trying to optimize the long-term value of its reward function. So today, first of all, we'll be talking about biases. What are biases? Can you remember in like kindergarten or year 1, you had problems like these? So, 2, 4, 8, what comes next? These questions always frustrated the hell out of me because I never really knew what they wanted. I mean, obviously, even if you take a sequence as simple as 1, 2, and 3, well, they could mean 4, but it could also be 5. This might be a sequence of Fibonacci numbers. It could be 2. The numbers could be a sequence of numbers dividing the number's position in the sequence. It could be all sorts of different things. Actually, there's an encyclopedia online called the Online Encyclopedia of Integer Sequences, and it reckons that there's 13,000 sequences of integers which contain the numbers 1, 2, and 3. Actually, there's an infinite number. And here's obviously some of them. So how the hell are we supposed to choose? But the important thing is that if you have no idea which one is the correct answer, you probably should first of all start assuming it's 4. And that's a bias. And that bias people call the no free lunch theorem. But that bias is really good and it's really important. Well, what is it? Why do we choose 4? There's 2 reasons. And there's 2 reasons that I'm going to be using in my AI. The first one is that 1, 2, 3, 4 is the simplest pattern. It just takes the least amount of time to explain. The numbers are just increasing by 1 each time. The second pattern, or the second bias, is that 1, 2, 3, 4 is just a very common sequence. You and I have seen it a lot of times before, and usually when you see 1, 2, and 3, 4 is actually the thing that follows. I'm going to rewrite these and call them the simplicity bias and the induction bias. So the simplicity bias is effectively Occam's razor. The simplest explanation is usually the best. Given a whole bunch of different choices, we should always be biased to assume that the answer or the explanation is the simplest one, given no other information. The induction bias is effectively just that patterns repeat. It's just that induction's true. And this is what we use when we do have additional information. When we've seen similar things before, we should be biased to assume that the world will continue to follow that kind of thinking. So in this case, the reasoning and the justification is that 1, 2, 3, 4 is just a common sequence. You see that sequence a lot. Hence, you expect to see that sequence in the future. There's an interesting result with this, which is actually really, really cool, which is that if you don't assume induction, there's actually no way to prove that induction holds. And that's something in Gödel-Escherbach, and I think I'll come back to that later, just because it's such a cool result. It's not mathematical, like proof by mathematical induction like you usually see in maths. It's actually what they call weak induction, which is just simple patterns. We use these 2 biases in different situations. When we have new things, we want to assume that the world's as simple as it could possibly be. And when we've seen things before, then we want to assume that the world continues to operate in the same way. So that is to say, weak induction holds. So I'm going to talk about the simplicity bias as it's used for this example. I won't talk about the induction bias too much. You can imagine, having seen the sequence 1, 2, 3, 4 a lot of times, that it kind of makes sense to assume that 4 is the correct answer just for that reason alone. And that's all that bias really means. So, why would we pick 4 over all of these others, according to the simplicity bias? Well, you can imagine the description length of each of these different patterns. For each of the different results this could be, there are patterns which explain why it should be that result. And those patterns have a certain complexity. So 5 natural numbers which aren't perfect squares, that's a pattern, and you can look at the description length of that pattern, or of that statement, and say that that's about how complex that particular pattern is. We can then reorder based on the length of these descriptions, and obviously 4 comes up the top. And if you actually have the numbers, this is the length in number of characters of each of these different patterns that we're seeing. This has a complexity theory name, which is the Kolmogorov complexity. So the Kolmogorov complexity is defined as the length of the shortest generating program in a given language. So if you have a pattern, or if you have a sequence, I can imagine writing a computer program explaining that pattern to a computer. And the length of that computer program is the Kolmogorov complexity. The problem you get, and you get the exact same problem with computer programming, is that there's a certain amount of assumed knowledge. And when are you allowed to use assumed knowledge and when aren't you? Because this changes the results a whole bunch. I looked at Wikipedia for the central binomial coefficients, and it looks like this. So you can imagine us then restating this to instead have this 49 and 62, the numbers of the description length to maybe include the Wikipedia page. But that doesn't really help you either, because the Wikipedia page itself is assuming a whole bunch of other knowledge about mathematics. The basic intuitive idea is that Kolmogorov complexity, it has this problem that if you have any of these different things we want to evaluate the complexity of, it's really, really hard to extract the new pattern that I'm trying to explain from all of the stuff you have to know to understand that pattern. And for that reason, it's very difficult to actually ever evaluate in any language the complexity of these different patterns. You could rephrase this as, instead of the simplicity metric being the complexity of the pattern, we could just say, well, it's the complexity of the pattern given some amount of assumed knowledge. So for your brain, what's the smallest leap that you have to make to be able to understand these different patterns? And we can say that that's the complexity. Then you have to assume some particular set of prior knowledge, but given that, then you can actually do this, and it works quite well.